Okay, geometers, so we move into chapter 4. Chapter 4 is still a neutral geometry chapter. We are still building a geometry that does not take a position with respect to Euclid's parallel postulate. We're still building with the 6 axioms we had put in place, and this is the first big theorem of chapter 4. The measure of an exterior angle of a triangle is strictly greater than the measure of either remote interior angle. So let me remind us what we mean by this. Um, so in high school geometry, you learn that you have some triangle ABC. Then we have to talk about what we mean by an exterior angle. When we talk about an exterior angle, we mean that we extend one of the sides of the triangle. So we find some point that's on the line that contains this segment, but that isn't between the two endpoints of that segment. And so the exterior angle is this angle. This is an exterior angle. Now, when you're in high school, you learn that the measure of this angle is equal to the sum of those measures. But that is equivalent to Euclid's parallel postulate. So our result is different. Our result says that this angle has to be bigger in measure than that one, and it has to be bigger in measure than that one. It's not necessarily that this is the sum of those two. That would be a Euclidean result. So that's just something to think about as we move toward the proof. So to do the proof, I'm going to restate the theorem slightly differently. I'm going to say if triangle ABC is a triangle and D is a point such that ray CD is opposite ray CB, then the measure of angle DCA is greater than the measure of angle BAC, and the measure of angle DCA is greater than the measure of angle ABC. ABC is a triangle. D is a point such that ray CD is opposite ray CB. Then the measure of angle DCA is greater than the measure of angle BAC, and the measure of DCA is greater than the measure of angle ABC. So here is the setup. Okay, let's walk through the argument. What we're going to do is we're going to find the midpoint of segment AC. We're going to call that point E. This is the midpoint of segment AC. We know that segments have midpoints. They are unique. So then what we're going to do is we're going to draw ray BE, and we're going to find a point F on ray BE such that E is between B and F, and such that BE is congruent to EF. That's our plan. That's our plan. We know that we can do this by the ruler postulate. We know that the line that contains BE is a number line. We know by the ruler placement postulate we can put 0 here, and then E corresponds to some coordinate. We can put a coordinate function on this line. And whatever coordinate E has, F is the point with the coordinate twice as big. That's the deal. That's the deal. So then we draw segment FC. Boy, that's a hideous segment. Wow, he has a YouTube channel? He's nuts. We know that angle AEB is congruent to angle FEC because they're vertical angles. And so we know that triangle AEB is congruent to triangle CEF by side angle side. And that means, and this is important, that means, I'll even change color, that's how important this is, that angle BAE E, which is angle BAC, is congruent to angle ECF. And notice ray CF is between ray CA and ray CD, right? Because F and D are on the same side of line AC, and D and B are on opposite sides of AC, right? Sorry, right? And A and F are on the same side of CD, because A and E are on the same side of CD, and E and F are on the same side of CD. So F is definitely in the interior of angle ACD. And so because ray CF is in the interior of angle ACD, angle ACF has a measure that's less than the measure of angle ACD. And that's what's established. That's what establishes that part. That's what establishes that part. Then we make a similar argument for why this is true by, instead of taking BC and extending it, we take AC and extend it. It's a similar argument using the other angles. So I'd encourage you to do that in the privacy of your home. But that's the argument. That's the deal. Okay? If I may, that's important because of this. For every line L and every point P, there exists a unique line M such that P is on M and M is perpendicular to L. You have previously proven that if point P is on line L, there is a unique perpendicular. You have proven that in a previous discussion, I believe. So the question is, what happens if P is here? What happens if P is here? Because if P is on L, then we're done. So what if P is not on L? So I'll again run through the basic idea behind the argument. We pick 2 points on L. We pick Q and Q, and Q prime. We don't worry too much about where they are. We know that there are at least 2 points on L. We just pick them. And we construct angle Q prime QP in 1/2 plane bounded by L. And we construct Q prime QR in the other half plane. Oh, this has got to go like so. In the other half plane, such that these two angles are congruent. And then we find a point P prime such that those segments are congruent. QP is congruent to QP prime. So just to build with rigor, whatever this angle is, whatever that measure is, we know by the protractor postulate we can come into the other half plane bounded by L, and we can make that angle on the other side. We know that the ray that does that is unique. Then we can take our ruler and we can say, I can measure QP, and then I can measure that far out on ray QR, and I'm going to call that point P prime. Okay? Now, incidence postulate says I can construct the line P prime, and I know that that has to intersect line L at a point F by the plane separation postulate. P is in 1/2 plane, P prime is in the other. So now I know that triangle PQF is congruent to triangle P prime QF by side angle side. And that means that angle PFQ and angle P prime FQ are congruent by correspondence. So those angles are congruent, and they are on a linear pair. They form a linear pair. And so they both must have degree measure 90. And if they are both 90 in their measures, then they are both right angles. And so this line M is perpendicular to line L. So the trick is, why is that unique? Why is this the unique perpendicular? Why can't there be another line that comes through and is perpendicular? Well, if that were the case, if there were another perpendicular line hitting at some other point R, then triangle PRF would have a 90-degree angle here, a right angle here, but then also an exterior angle that was 90 in measure, and you can't do that. The exterior angle must be greater, the measure of the exterior angle must be greater than either of the remote interior angles. So it's not possible for a remote interior angle to have measure 90 if an exterior angle has measure 90, and so that's the contradiction there. Okay? Okay, very good. That's the exterior angle theorem and why it matters.